Hi. In this video, I would like to talk about model confidence, and in doing so, I also hope to talk a little bit about algorithm design. After all, there is more to an algorithm than just the accuracy scores that come out of it, and it's this design aspect that deserves to get a little bit extra attention. Now, to be specific, I will be discussing the diet architecture that we are using in Rasa, and I'll also be talking about a small improvement that the research team has recently made. I will, however, only zoom in on a very specific portion of the algorithm, namely, just this bit. If you're a little bit unfamiliar with diet, however, you don't have to worry, because what I'll be talking about here is something that's a little bit more general than just our specific implementation. So let's zoom in on what I mean by that. Now, at the very end of our classification algorithm, we have two embeddings. One embedding belongs to the utterance that the user has just mentioned, and the other embedding belongs to a intent label. And yes, there's an entire process that happens before these two embeddings. Specifically here, we've got a transformer layer in front, but let's ignore all of those details for now. I'm talking about a neural network here where the label is encoded in an embedding and I've got a representation of text that needs to be classified. Then a typical architecture choice would be to say, well, let's take those two embeddings, let's then calculate a similarity between these two embeddings, and then we might use this to calculate a specific loss value. Now, when you look at just this part of the architecture, you might not be entirely impressed. After all, it's just two dense layers that are performing a embedding, as well as a similarity, but you'd be mistaken if you were to take this for granted. Because we're at the end of our algorithm here, we can assume that the labels and predictions are going to be mapped together at exactly this point of the algorithm. It's from here where we can expect gradient updates to happen, which will propagate back to our embedding layers, but also everything else before. And with that in mind, I do hope it's very clear that the choice of the similarity measure, as well as the choice of our loss over here, will have a very significant effect on everything that is happening. Now, this observation allows us to take a step back and to really ask ourselves the question, what properties we're interested in here? And of course, one property here would be to say, well, we want to have high accuracy. That's, of course, still valid. But maybe it's easier to reason about the properties that we're interested in if we consider these two embedding layers and what they will do. By zooming in on what's happening there, we might be able to make some good algorithmic design decisions. Now, I'll make a low-dimensional analogy of what we might want to have in our embedded space. What the embeddings will do is they will map labels and utterances into some high-dimensional plane. I'm not able to draw in a high-dimensional plane, so let's just pretend like we have two-dimensional embeddings, and we can then start to wonder what sort of properties we would really like to see in them. Let's have this blue dot be the current utterance, let's have this green dot be the correct label, and let's have this red one over here be the incorrect one. Well, what I hope you would agree is that if there is a embedding over here for the correct label, then you would hope that the embedding for the current utterance is close to it. You would really like this distance to be small. You would also hope, though, that the distance from the current utterance to an incorrect embedding, that is big. And now that I'm thinking about this, I hope you also agree that we would really like the distance from the correct intent to a incorrect intent to also be big. And now that I'm thinking further, I think you would want to have the distance between all embedding labels to be big. And we can also imagine that if we have an utterance that doesn't belong to the current label, that we would also like that distance to be big. Looking at this, you might be reminded of the starspace algorithm, and you would be completely correct if you were to point out that in order to get to these similarities over here, we would have to do some negative sampling of both intents as well as utterances. However, the main conclusion I hope you have at this point is that it deserves to think about what similarities we will be applying. The type of similarity measure, as well as the loss function that might follow, will have a huge impact on the embedded space that we will end up with. And this embedded space at the final edge of our algorithm will have a huge impact on the predictions that go out of the model. But the impact really goes beyond accuracy. Because if I think about what I'm interested in a model, it really isn't just accuracy, it's also if we have a good measure of confidence. Whenever we make a prediction, we would like to have a reliable confidence measure. And how do we get this reliable confidence measure? Well, by thinking about what similarities mean in this embedded space. And with that in mind, let's zoom in on how we might be able to translate similarities in this embedded space into a confidence measure that the model outputs. If we think very carefully about this, we might get a very nice property indeed. So let's think about ways how we might get embeddings, like drawn below, into something of a confidence measure. Typically, when you have embeddings, you can think of them as vectors. Let's say I've got this vector from the origin to my utterance embedding. Then in this case, I might be able to calculate a similarity by calculating the dot product between this vector and for all of the vectors belonging to all of the intents. I would calculate the dot product between u and intent number 2. I would also do that between u and intent number 1, and between u and intent number 3. Now, a thing to remember with these distances is that they don't necessarily represent a probability. We have a dot product, and this dot product is theoretically unbounded. And even if I were to pick another distance measure like cosine distance, then sure, I would have a distance measure that isn't so much bounded, but it still wouldn't represent a probability. So commonly what people would do is they would take a distance measure like dot product, and they would pass that through some sort of activation layer. One popular candidate would be to pass it through the sigmoid function. And the idea here is that indeed we can map any values between 0 and 1. However, if you start looking at the sigmoid function critically, then you might notice a few oddities. Let's say I have a dot product of -4 and another dot product of -3. And I'm going to compare that to two other dot products, one of -.5 and one of +.5. Well then, in both scenarios, we have the same difference in embedded space as far as similarity is concerned. But if I were to actually compare the difference in the output of the sigmoid, then I hope you would agree that this difference in similarity doesn't equally translate into a difference in confidence. If we're measuring near 0, then odds are that we're going to see a much bigger difference compared to if we were on the outskirts. And if we were to take somewhat extreme values here, let's say that we are comparing +10 with +15, well, then we get this awkward scenario where there's barely any difference at all. Even if in embedded space we would argue that we have a difference in similarity that's quite high, this wouldn't automatically translate into a difference of similarity as far as this sigmoid is concerned. So this might make you wonder, well, is the sigmoid here really appropriate? Is the output here really a measure for confidence? And this might make you consider, well, let's do something else than sigmoid. Let's take another popular choice. Let's go for softmax. Softmax is a popular final layer, and a property that this one has is that it can translate inputs to something that sums up to 1. However, here, if we have a sequence of similarities, let's say an array with 1s, and if I were to compare that to another array, again, where we might have similarities, but all of these would have a higher number, then the softmax, effectively, considers them equivalent. Now, I hope you would agree that all this activation business is a little bit awkward, because these probability values matter when we are interested in triggering a fallback. We would really like to have a mechanism that can translate the output of a machine learning model into a value for confidence. And maybe now we can ask a very good critical question. Do we really care about having a confidence measure being between 0 and 1? Maybe we don't have to do this translating from this embedded space similarity into something that looks like a probability distribution. Because similarity in this embedded space is what the algorithm is actually optimizing during training. And because of that, it might make more sense to use this dot product or maybe the cosine distance as a confidence measure, instead of forcing it to become a probability via something like softmax at the end. Now, this idea is something that some of my colleagues from the research team have been investigating, and we have found evidence that indeed it might be worth it to consider these kinds of similarity measures as a measurement for model confidence. So let me show you the results from one benchmark. What you're looking at here is a chart that you can get when you run the Rasa test command from the command line. What you see is the confidence score over here, and we plot that against instances where we got a intent prediction correct versus a intent prediction wrong. In general, you can see that when we get it correct, really we get a lot of confidence. All of the values are near 1. However, you also see that the same thing is happening here. And sure, the axes at the bottom here are a little bit different, but if we're interested in finding a good threshold for a fallback classifier, then we don't want this thick bar over here. We would prefer to be able to say something like, let's put a threshold on this end, where everything with a confidence below this value will automatically be triggered as a fallback. In this particular run, though, that's very hard, again, because of this very thick bar over here. So this was the before scenario, and what I can do is I could compare this to maybe using a confidence value that's based on the cosine distance, as opposed to something that's been normalized beforehand. So here is the same chart, but for the cosine distance confidence measure. Theoretically, these numbers that you see over here could be between -1 and +1, but the main thing that I hope that you see that's different is that the distribution over here is a lot more spread out compared to over here. Again, it would be good to observe that the x-axis here isn't exactly the same as over here, but again, I do hope you observe that it's easier in this scenario to pick an appropriate fallback threshold. As a final comparison though, here's the chart when we are using the dot product of the final embedding layers as our confidence metric. You should now clearly see that the numbers over here are no longer between 0 and 1, but moreover, we really see more spread. In this situation, because there's more spread, it seems like a more meaningful exercise to find an appropriate threshold value for a fallback mechanism. We are making this feature available in Rasa right now, so that means that if you would like to configure your diet classifier to use a different confidence measure, that you can do so as of the new release. Note that we think that there is merit to the cosine model confidence measure, which is why if you run Rasa init, this will be the standard diet classifier setting as of right now. However, if you aren't running Rasa init, the default parameters are kept the same. If you are currently running the diet classifier like this, then you don't need to worry. We won't change any default parameters unless you explicitly change them. The reason why we are doing this is that we can certainly imagine that if you are used to a confidence measure always being between 0 and 1, that it can be quite a lot to take in to suddenly see these values shift. Depending on the confidence measure that you are using, you might see different results, and we can imagine that it takes some time to get used to. That said, we highly recommend everyone to try out these new settings, because we've been impressed at how this cosine similarity really seems to quantify confidence in a better way. We think it will help you find more appropriate thresholds for fallback classifiers, but as always, feedback on this new feature is definitely appreciated.